Hello, everybody. I'm Connor Childers, and this is my co-op 2020 experience at Altec. So my role at Altec was that I was hired to be a product engineer, which was in the design department. And basically what we did was we evaluated work orders that were sent to Altec from a customer, and these work orders had all of the specs and other things that they wanted on their bodies. So what the designers did was we put all of these specs in a 3D assembly of the actual service bed, and we did all of this on SolidWorks. I don't actually have the SolidWorks models or the work orders to show, but we also worked on three projects while we were there. And other two, I wasn't able to show because it has some confidential things in there, and my supervisor told me that I could use this one. So this is going to show kind of what I contributed to the company, and other than actually making the bodies for the trucks. And so this is a project that I did on E-Track rating, and the E-Track you'll see it in the next couple slides and kind of explain how or what it is if you don't know what it is. And so this is going to explain just what I did in the project and the outcome that I got from it. This is the scope of the project, and so this project was to test the E-Track and for our applications, so for Altec's applications, and to produce a rating. And so for Altec's applications, it was meaning that for how to see how strong with the E-Track mounted on one of the panels that was used, to see how strong the actual panel and with the E-Track on it, like how much that it could undergo. And so I was going to test this using a pull tester, and by welding the E-Track to what would be compared to the inside of the cargo area. And so from the picture that's going to pop up, you can see where the actual cargo area is and the horizontal on the horizontal, which is the horizontal compartment. So where the horizontal door is on the inside area is where the E-Track is usually mounted. So that's where I'm testing it. But that's what I'm going to be comparing my test model to. And so the deliverables, obviously, rating for the E-Track, and this is going to allow the customers to know how much stress this E-Track could undergo before that there's any deformation or failure. So the justification of the project, was currently not a rating for the E-Track for the applications of Altec, and this made it really hard for customers to be able to tell how much force they could apply to the E-Track whenever they were strapping something down or anything like that in the back of the truck. And so this would help the customer to know that, and also had some constraints, and they were time because we didn't have. I think we only had a couple months to do this, and that we couldn't have any design changes to the E-Track itself. It was only testing the strength of it. This is the design concept that I came up with for a jig that I was going to put in the pull tester, and I was trying to simulate the E-Track welded to the back of a horizontal, like I explained a little bit earlier, and the channels that are on the right and the left underneath the horizontal panel are are trying to simulate the center partitions, so the which are the inside panels on in the horizontal compartment. So what separates the a vertical or each compartment from the other compartments, and this would allow me to get more accurate results. And the other two channels on the bottom, and then there's another one on on the back side connecting the two, those were just those allowed me to mount it in the actual pull tester, so they didn't really have anything to do with the horizontal or anything like that. It was just for mounting purposes. So I did some FEA or finite element analysis before I actually did the physical testing, and I got up to we were trying to see when it was going to get to a quarter inch of deformation. So that was kind of just like the standard that I was following, and that's what Altec was wanting me to look. And then also they were wanting me to see when there was going to be permanent deformation. So it got up to 180 pounds on the sixth bracket cut out from the edge. So, or from each of the edges. And then I also did one in the middle, but we'll get there in a second. And so it was fixed on the sides where the panel is welded to the channels. And that's where these green arrows on each side on the left and right are. And it shows that there is the most stress is actually on the E-track itself. And there was also a lot of strain on each object when the force was applied. On to the testing. When I actually did the physical testing of the left side of the E-track, it got up to 180 pounds, like the FEA said, and but it deformed more than what the FEA would said. So the deformation on for the physical testing actually got up to 0.252 inches, and you can see from the chart just that the more load, then the more deformation, which is what you would expect. And then here's also a picture of the testing, and you can see the little bit of deformation that there was. This is such a long piece, and I was making it the longest of what a horizontal would be, and so you can actually see the deformation of when it's only a quarter inch. So for the right side of the E-track, it was able to hold a load that was a little bit higher than the left side. I'm not really sure what the reasoning for that is, other than it could have possibly been just the welding or where the welding was placed when welding the E-track to the panel. And so you can see that the load got up to 200 pounds, and it deformed 0.253 inches. And here's another chart, which is basically the same thing, just kind of showing how it jumped up in each increment. And then here's another picture of the physical testing, and you can see that you can still see the bulge in the metal on the right side as well at 0.25 inches of deformation. So for the center, I also did FEA, and so the center is going to be the weakest point on the panel and the E-track, and since it's so long, it's going to end up being very weak. So this is where I wanted to test it here just to see how much this actually could take. So at its weakest point, how much force would be able to take before it deformed too much. And it on the FEA showed that it was only able to get up to 155 pounds. And same setup, they were fixed on both sides where the panels are going to be welded to the channels, and it deformed 0.254 inches. And like the left and right sides, most of the stress was on the E-track, and there was also a lot of strain when the force was applied. For the physical testing of the center bracket on the E-track, the FEA was a little bit off, showing that it would get to 155 pounds, but it actually was only able to get up to 120. And so you can see by this chart, it's kind of the same thing. As the load gets higher, the deformation gets higher, but even though it was only able to withstand 120 before getting to about a quarter inch of deformation, it was able to withstand 1,200 pounds of force and before it permanently deformed. So, and even when it permanently deformed, it was only a 16th of an inch off. So I would say it's pretty impressive. And so you can see by the picture here, this is the 0.258 inches of deformation, and you can see the little bulge in the metal again, but it's not too bad. And then another picture of the 1,200 pounds of force on it, and you can see it's a lot of deformation. Um, I'm not really sure how much there actually was. It was almost too much to calculate on this meter right here, but yeah, it only ended up staying about a 16th of an inch off after we let go of the load. My observations were that it didn't take much to get to a quarter-inch deformation, and it was that the FEA and the physical testing were very similar, um, but it didn't take, or it took a lot to get the permanent deformation, which is honestly the most important part. So, and like I said a second ago, it got up to 1,200 pounds. Like, that's a lot of weight for only a 16th inch of permanent deformation, and the metal was 14 gauge metal, so it it's pretty thin, and so the 1,200 pounds is actually pretty impressive. But the recommendations that I have is that rating the for Altex applications to be 400 pounds, and with that makes the factor of safety 3-1. So looking back at this co-op, this was my first co-op that I did, and it was a really good experience. It was last summer and then into the fall. So I went in and I started working in June, and we ended December 4th. And I did enjoy the time working at Altec. It was a very good experience. All the management and other employees worked really well with the co-ops, and uh, they were just it was just a good environment to be in. The Being with COVID, it we worked from home a little bit, which was we didn't really get the chance to work with a lot of people for a good bit of time. But when we started working on our projects, we were able to get back in the office and be around more people. So it wasn't too bad. But I initially wanted when I graduated to go into design, but after working at the design co-op, I don't really think I want to do that anymore. Not that it was bad, but I don't know if it's for me. I do enjoy designing, but it seemed to be just more behind the computer and not a whole lot of hands-on work and actually being in the field. This isn't probably how all design jobs are, but this one in particular didn't. It really didn't suit what I was wanting to do, and but I did learn a lot of new things, and like majority of it was just working on SolidWorks, and because that was a new software for me, I was just used to using Creo or AutoCAD because that we used Creo here at UNC Charlotte, and uh, but also just learned how to manage my time because we had deadlines to make or to meet, and uh, it was just overall it was a really good experience. So I just want to thank everyone for coming and listening to my presentation, and here's my contact information if you want to get in touch with me, and just if you have any questions, go ahead and ask away.